Hey everyone, welcome to Exam Blueprint. In this video, we're going to be studying the chapter solutions, Class 12 Chemistry. So, assemble. If solutions feels formula heavy or confusing, take a breath. In the next few minutes, we'll finish this entire chapter in a structured and exam-focused way. Concepts first, then formulas, then applications. Keep your notebook open. Let's begin.
Have you ever thought about what connects the fizz in your soda, the dangers of scuba diving, and even the air on a mountaintop? Well, believe it or not, there's a hidden scientific law that links them all, and it all comes down to the chemistry of solutions. So let's start with a bit of a puzzle. What on earth could a can of soda, a deep sea diver, and a mountain climber possibly have in common? I mean, they seem like they're from completely different worlds, right? But they're all connected by the very same fundamental principle.
And the answer is the science of solutions. Yep, this one little corner of chemistry explains all of them. And by the time we're done here, you're going to see exactly how it all fits together.
To really get it, we have to start by realizing that the world around us is, well, it's messy. It's rarely pure. We live in a world of mixtures.
Just think about it for a second. We don't really find pure gold or pure iron just lying around. Instead, we use alloys like brass. That's a mix of copper and zinc, or bronze, which is copper and tin. Our own bodies are incredibly complex mixtures. Our blood plasma, for instance, is basically a salt solution. And it's the unique properties of these mixtures that make them so incredibly useful.
Okay, so to wrap our heads around this, we need to build a little toolkit. Let's make sure we're all on the same page with three key terms: solution, solute, and solvent. First up, a solution. Now, the official definition calls it a homogeneous mixture, and the key word there is homogeneous. All that really means is that the mix is perfectly uniform. You can't see the individual bits. It looks and feels exactly the same all the way through.
You see, every solution has two parts. You've got the solvent, that's the main ingredient, the one you have the most of. It's the thing that's doing the dissolving. And then you have the solute. That's the stuff that gets dissolved. So if you stir sugar into your coffee, the coffee is the solvent, and that sugar is the solute. Simple as that.
And here's something that might surprise you. Solutions are not just about dissolving solids and liquids. As you can see here, they exist in every state of matter. The very air we're breathing right now, that's a gaseous solution. The oxygen that fish need to live, that's a gas dissolved in a liquid. And metal alloys, those are actually solid in solid solutions. Pretty cool, right?
So, if pretty much everything is a mixture, how do we talk about them with any precision? You know, just saying a drink is sweet or not very sweet isn't going to cut it in science. We need to be able to measure the mix.
And for this, chemists have a whole toolbox of different units to express what we call concentration. You can think of these as different kinds of rulers. Each one is perfect for a specific job, whether you're working in a factory, a pharmacy, or a research lab.
Now, we're not going to go through this entire list. Instead, let's just focus on one that's really useful for talking about tiny, tiny amounts, parts per million, or as it's often called, ppm.
1 part per million. It sounds incredibly small, doesn't it? It's kind of like one single drop of ink in a giant kitchen sink full of water. But can an amount that small actually make a difference?
Oh, absolutely. It turns out that a concentration of just 1 part per million of fluoride ions in our drinking water is enough to make a massive difference in preventing tooth decay. It's a perfect example of how sometimes incredibly tiny amounts can have huge, huge effects.
Okay, so let's bring this all back to our big puzzle. The core idea we need to unpack is all about how gases, specifically, dissolve into liquids.
Which brings us right back to our first example. We've all been there, right? You crack open a can of soda, you hear that classic psst. And if you leave it out for a while, it just goes flat. But why? What's actually happening?
Well, the secret lies in the relationship between two things: pressure and how well a gas can dissolve in a liquid, which is a property we call its solubility. This relationship was figured out by a guy named William Henry, and now it's known as Henry's Law. And what it says is actually pretty simple. The more pressure you put on a gas that's sitting on top of a liquid, the more of that gas will dissolve into the liquid. It's a direct relationship. You double the pressure, you can dissolve double the amount of gas. And this whole relationship can be summed up in this neat little equation. But you don't have to worry about the math. All this really shows is that pressure and the amount of dissolved gas are locked together. When one goes up, the other goes up. More pressure means more gas gets dissolved. It's really that straightforward.
All right,
This is where it all comes together. That one simple law is the key that unlocks all three of those seemingly random things we talked about at the start. Let's connect the dots. First up, the soda. To get all of that fizzy carbon dioxide gas into the drink in the first place, manufacturers seal the bottles under really high pressure. Henry's law tells us that high pressure forces more of that gas to dissolve. That's where the fizz comes from.
But the second you pop that top, you release all that pressure. That psst you hear? That's the sound of the pressure inside the can suddenly equalizing with the air in the room. All at once. The liquid can't hold on to as much CO2, and so the gas makes a run for it, escaping as bubbles. Leave it out long enough, and all the gas escapes, leaving you with sad, flat soda.
Now let's look at the scuba diver. Deep underwater, the pressure is immense. The diver is breathing compressed air, so just like the CO2 in the soda, more and more nitrogen from the air dissolves into their bloodstream. Now, if they come up to the surface too fast, well, that's exactly like opening the soda can. The pressure drops rapidly, and the nitrogen comes rushing out of their blood, forming dangerous little bubbles in their joints and tissues. This is what's known as the bends, and it's incredibly painful and can even be fatal.
And finally, our mountain climber. Up on a high mountain, the exact opposite is happening. The atmospheric pressure is much, much lower than it is at sea level. So, following Henry's law, this lower pressure means less oxygen can dissolve from your lungs into your blood. This shortage of dissolved oxygen is what causes altitude sickness, or anoxia, which leads to that feeling of weakness and confusion.
So there you have it. From a simple can of soda to life-or-death situations for divers and climbers, it all comes back to Henry's law. It's just a powerful reminder of all the invisible chemical rules that are constantly governing our world. And it leaves you with a final thought. If this one simple law can explain so much, what other hidden principles are shaping your reality right here, right now?
If you revise these formulas and practice a few numericals, Solutions becomes one of the most scoring chapters. Don't just watch, write once. Practice twice. Next video, we continue the sprint. This is Exam Blueprint. Structured prep, real results.